Welcome to Happy Path Programming. I'm Bruce Eckel.
I'm James Ward.
We are now podcasting with new and we hope improved equipment.
Fancy headsets.
Yeah. With mics that should reduce echoing and give you a more pleasant listening experience.
Let's hope so.
That is the hope.
Yeah.
But
let us know.
Yes, let us know if you like it better. So we have a topic list, and we're going to read the topics ahead of time so that you have the option to say, nope, I don't want to listen to this podcast.
Oh, that's a good idea.
Yeah.
Give people a heads up.
Yeah. Our goal isn't tricking you into listening to the podcast.
Should we leave like a cliffhanger to keep people listening till the end?
That's what normal media would do, but
that's right.
We're
not normal.
This
media.
Is the happy path.
That's right.
So our topics are, and we might not get to all of these, very, very possibly.
We'll just see how tired we get.
Yes. So what would a language be like if we didn't have to constantly think about efficiency? And then talking about languages created for development speed versus languages created for reliability. We're sort of focused on reliability now, so we're thinking about that. I've come up with a new monad description that I want to try out. What are the advantages of using error monads over using exceptions? And we'll explain that when we get to that point. We've sort of realized that type classes are kind of like default arguments. So we want to know what are the problems that default arguments don't solve that type classes do. And then finally, we got a question from someone who's just been out of college for a couple of years about design patterns. How important are they? Which are the best ones, et cetera, et cetera. So we may get to that as well.
Awesome. Looking forward to it.
Okay.
Let's go. Okay. So languages and efficiency. It feels like a lot of stuff we do in programming is done for efficiency. We do mutability, allegedly.
To save memory.
Mm-hmm. We, as a developer, have to think through how large is my data set that I'm doing some operation on, right? Can it fit into the memory that I have available?
Yeah, like the Julia language was designed partly around this idea that you're going to have so much memory that it's going to overfill your RAM, and that's going to affect how things work. And so it's designed to help compensate for that. But actually, I'd say it was designed so that you wouldn't have to think about that as much.
Yeah. I mean, isn't garbage collectors maybe like one of the ways that a language said, all right, we're gonna make this part of efficiency something you don't have to think about?
That's a good one, because when you look at Rust, it says no garbage collector. You have to have this.
It's a human garbage collector.
Extra overhead. Well, it's like what we used to have is the bad human garbage collector. This is a good human garbage collector.
That's right.
So you have to have some extra programming overhead, and I hear that once you get used to it, you don't think about it very much. But that is to eliminate the garbage collector to make the program more efficient.
Yeah.
So that's which one? We got garbage collectors because, at least with some languages, it was so hard to think about how do I clean things up. I mean, like if you have a collection that has references to other collections, all of a sudden it gets
no
really
demarcation of boundaries about where this thing could be used and how far down the call chain it goes. And
it was kind of an afterthought. It was like, oh, well, the programmer will take care of cleaning up memory. And it turns out then we discovered that, oh, that's not always possible if the language doesn't have this built-in support for it. Yeah. So what Rust is kind of going back and it's saying, all right, we'll have the built-in support for the programmer keeping track.
That's right.
So that
we're going to make the programmer demarcate the kind of boundaries of usage of these things.
Mm-hmm.
Whereas and garbage collected languages say, all right, you developer, you don't even have to think about this. We're gonna do it. And we may not do it as well as you could do it if you did it manually, but it'll likely be good enough.
Yeah. And in many cases, it can be very
In many,
fast. I
yeah,
mean, there's certain optimizations that can be done, and we don't have to think about that. Garbage collection is taken care of for
yeah,
us.
yeah,
So, um,
yeah. So I think there's maybe we've seen with garbage collection some some way that the language has been impacted by making the developer not fully responsible for efficiency. And there's probably other places where this has happened, but what I wonder is at what point can we add that same construct to other language pieces like immutability, and maybe maybe the compiler or the runtime or whatever can do nice things if it knows that everything is immutable to make things more efficient,
oh,
so that you don't take a hit on efficiency by being immutable.
yeah, there's other. So I have had experiences over time because I started in assembly language and, I quote unquote know how all the low level parts are working and how expensive they are, et cetera, which is an illusion.
Yeah.
But because I carried that baggage with me, I would get into a language like Python, and I would assume that one construct would be inefficient and say, oh, well, I should write it this more complicated way. And almost inevitably, the more complicated way was not only harder to read, but it ran slower.
Yeah.
And so I would learn to trust Python's, like, do the simplest thing. It's almost always going to be the fastest. And then,
And likely sufficient for what you need.
yes, very likely, pretty much always has been. Um, and so, I mean, there's that end. And then as I'm going through the functional programming and Scala book, there's a lot of consideration for efficiency throughout that book. They say, this is more, you basically have a lot more control over the efficiency by the way that you write the code.
Yeah.
And you kind of think, oh, that's using mental overhead, but maybe it's only using it on the lower level when you're creating like the various folds and flat maps and things like that. And then once those are there, then maybe you don't have to. I mean, I haven't gotten to the point where we're building bigger things. Do we think about efficiency at that point or not? I don't. I haven't gotten there yet.
Yeah. Yeah. Yeah, it seems like there's a kind of always this constant balance happening between allowing the developer to be expressive and not have to think about efficiency versus, oh, there's a time when the way that that was optimized by the compiler or runtime was insufficient for my use case. And so now I have to peel back the layers and figure out a way to make that thing more efficient because it wasn't as efficient as I needed it to be or something. But
Well, like tail recursion is
yeah,
you. I didn't understand, why do we worry about this? Why do we think about this? Well, because you're going to blow up your stack. Otherwise, it's not even an optional efficiency. It's your thing doesn't work if you don't
that's right.
do
This
the
is going
tail
to
recursion.
blow up.
Yeah, and you have to write your code in a particular way to
Yeah.
enable the tail recursion optimization.
Yeah. Like we talked about with Dick last week, 2 weeks ago, was around laziness and how most languages are eager by default and some have a way to be lazy if you want. But ideally, it's lazy by default and eager is, when you need it. And so I think that's one place
Well,
where
it wouldn't even
languages
have a
could,
sense of eagerness in that case. It would just be, we're going to wait to evaluate this thing until you actually do it. And if you never do it, we want to evaluate it.
yeah. Yeah. And in Scala, there's a lot of places where I think about, okay, this value on this particular call chain, it doesn't need to be computed, but on this call chain it does. And so then I make it a lazy val. But that's something I have to think about is like, oh, given the execution structure of my application and different paths that I go down, do I want this thing to be a lazy val or not? And it's like, why am I making that decision?
Well, and another case is you can have a function that tends to evaluate if it's got two arguments, tends to evaluate the left argument first, and then or the right argument first. But then you can also have a balanced one, which is ideal for forking off different processes to solve these things, and you have to make it that way.
Yeah.
And when you're looking at it, you understand, oh yeah, I have to think about this here. But your question is, wow, wouldn't it be nice if we could just think about what we're trying to do and not the
The resource constraints.
the resource constraints?
I think a lot of it comes down to resource constraints, whether it's CPU or memory or network or whatever. It's like, I've got a finite number of resources. How do I fit what I'm trying to do to work with that? Or maybe there's a future like with Ponylang or Unison or something where let's just imagine we have infinite resources, and if my program can transparently distribute across whatever it needs to do what it needs to do, then the programmer shouldn't ever have to think about any resource constraints.
Right. And if you look at the actor model for objects, you go, well, I just send requests all over the place. The only constraint that the actor has is it has to be able to catch that request and store it, but it does that with the a little tight loop at the front.
Yeah.
And then at some point later.
So Akka does this where you send a message to an actor, and that actor could be somewhere else on the network. It doesn't have to be in the same machine. But as a developer, you have to actually decide. It's like local and remote EJBs. You have to decide, is this thing remote or not? Where does this actor live? And for efficiency, you want things that are low latency to be on the same node, the same machine, and things that maybe don't have the same latency requirements can be remote, or things that you need to scale beyond what a single machine can do need to be remote. But again, the developer has to decide where these actors live. What would be ideal is, why can't the system figure out that for you?
It may, well, similar to the actor model and its constraints, it may require further changes or constraints on the programming model.
Well, and I think that's what Pony was trying to do, was put some of those constraints that it needs to know about into the language, so that then it can decide where these things live and what the life cycle is and how many to spin up and that sort of thing. So yeah. So I think there's evolution happening in this area. I think that Heather, who used to be on the Scala team, is now doing research into specifically this area. Heather Miller, around, can you create distributed programs that the system is handling the distribution and resource allocation for, not the developer?
Yeah.
So I think there's some. I don't remember if she's at Cambridge or I don't remember where she is, but I think she's one of the people that's investigating this idea. So hopeful that, let's say 15 years down the road, we hopefully won't need to be making so many decisions as developers about resource constraints. I guess one tricky resource constraint is time. Like, that's not one that we don't have an infinite supply of time, and users aren't willing to wait for an infinite amount of time. And so that time is a resource that, as a developer, you do need to think about. It's like, I could do this operation and it may take 1,000,000 years to complete. Is the user willing to wait 1,000,000 years? Probably not. I probably need this to come back. I need a response back from this computation in, let's say, 100 milliseconds. And so maybe that's a resource constraint that you'll never be able to alleviate.
Well, and that comes up sometimes. It's not constantly in the forefront of your, when you're thinking about programming.
Yeah.
So, but that actually, I think that sort of segues us into our next, certainly programmer time. And that's another issue that we have to think about. How long does it take to develop an app? And this week I thought of something. I thought of a concept which I think I called uh, I don't know, the statistical success of an application. It's like it's not bug free, but it does enough that it satisfies enough users that it's quote unquote successful.
Right.
It's
Yeah.
not absolutely reliable, but we can develop it fast enough.
Yeah.
And that's the idea of like, well, a lot of our languages, I think, have been created. In fact, I think oh, yeah, back about when I was graduating from college,
Yeah.
there was this idea of the software crisis,
Huh.
which is we needed to develop more software, but you know, it took too long to do it, and that was the crisis. And I think that
We were always falling behind, further
we're always
behind.
falling behind, and so we ended up creating languages that could develop software quickly, but they weren't really focused on reliability. They were focused on fast development.
Right.
And I think we've been going down that path for a long time. And
Yeah.
and our reliability is kind of on the back end. All right, well, some from type systems as we add them on. Like Python now has optional static typing, which makes it more reliable.
Yeah.
But then we rely on testing, and testing is never. How can you make it completely reliable?
Yeah.
You're assuming that there are bugs in there, and this is a sieve to which you're trying to find those bugs, but
Yeah. Yeah. I mean, you look at Rails, and Rails, I think, is a very good example of a language and a framework that made efficient or made developer productivity, made the speed of development very fast. But I think if you have gone that route, you likely have some reliability issues, or maybe you can't refactor your code or add features. Maybe your velocity slows down at some point because of that initial speed. And so um, I think we've kind of seen this as a dichotomy. You can either have developer efficiency or you can have reliability. And one of the things I've wondered about is, are these convergent? Like, are they ultimately coming together, and can we get to higher reliability without sacrificing that developer productivity? And I think that we've seen pieces of that, but there's also a question of like, how much reliability do you need? Are you building a spacecraft that's going to go to Mars? It's a different level of reliability than
a web
a web,
server.
yeah, some, any given software that you and I tend to
Mm-hmm.
work on. And so,
Well, the
but
customer would say, I know it's just a website, but I still want total reliability.
right, yeah, yeah, for sure. Yeah, and then and so we can put some of that onto tests and process and CI/CD and some of those things. But I think you and I have pondered a lot is like, can the language and frameworks give you better reliability while without sacrificing the productivity? And that's what we're kind of exploring in our book in a lot of ways. But
At least that's what we think we're doing now.
yeah,
We'll see where it takes us. And as I've been going through the functional programming and Scala book, they're spending a lot of time developing these small pieces. And so my impression is, oh, it's going to take a long time to build a reliable program. But then this morning you're telling me, oh, that's what, for example, Zio is. What once you get the small pieces in place, then you have the reliability and you can compose them more rapidly and know that each composition is of reliable pieces is also reliable. And so we can.
that's a good way to look at it, is in terms of composition, because if you take something that is, let's just throw a number, 90 8% reliable, or this given component 98% reliable, and then you compose it with another piece that's also 98% reliable, then aren't you down to like 96% reliable?
Yeah,
Like
as
there's
you
some.
combine the pieces, the reliability, it's a multiplicative effect, it
Yeah,
appears to be. So,
it seems to be. And yeah, I think with effects, we start with something that is a lot more reliable in and of itself, but then I wonder if that multiplicative effect doesn't hit us as much, or maybe it's just that we're starting with a lot more reliable foundation or something. So
I mean, if you take a pure function and a pure function and you combined it, you're going to
get a pure function.
right. So that, like, as long
Yeah.
as you're dealing with pure functions, and I mean, I'm still getting used to this, but I think what the effect is it says, all right, cool, you got pure functions over here. Here we have the effects, how we manipulate the world or how the world manipulates us, or error conditions. And what we're going to do is we're going to restrict the impact of those so we can maintain control on them. So we can still use our pure functions and have the reliability of those. And then the effects aren't going to get out of control and impact the whole system.
We just move all
Something
that
like that.
to a thin layer that is outside of all the other stuff.
Mm-hmm.
And so you've got all your logic and your um, wiring of things together and your retries and all that kind of stuff outside of the actual definition of how you talk to the outside world. And that allows you to have much better certainty that that core, that pure core, is fully reliable.
Mm-hmm.
And yeah, you could have uh, unreliable pieces in that thin outside effectful piece, but you've really isolated that to to a thin layer.
Mm-hmm. Yes. Well, I'll understand more about that as time passes.
Yeah, yeah, and I think to the initial question of like how much could a new language make this better? And if we look at like what Unison is doing, I think that it is defining a language that does a lot of this reliability stuff, just kind of core to the language, the effect stuff. I need to look into how they actually do effects, if they use like effect monads, or if they use algebraic effects, or
Mm.
how they do effects. But it definitely is something that they've made conscious decisions to do this well. Whereas I think most other languages that we've seen don't consider this aspect to separating effects
Mm.
from core stuff. They just don't think about it. It's not part of the programming model.
So I think we could probably summarize the question of, can we increase our efficiency, our programming efficiency, even though we're using these things to create reliable systems? And the answer is maybe we don't know yet, but it's possible. And because if you think about, well, how much less testing do I have to do? How much more quickly can I put these pieces together?
How much more easily can I refactor things?
Well, yes, there's the refactoring
There's,
issue.
yeah, there's like
So,
the library side of things,
mm-hmm,
where it seems like from Zio, the library ecosystem that's evolved around it has has grown very quickly, because if once someone creates a Zio thing, it's very easy to compose that Zio thing that's talking to whatever system or doing whatever it wants. It's very easy to compose that into your Zio system. And so there's a nice model for encapsulating pure functions effects in Zio, and then reusing those in a really nice way that you have expectations around how the thing's going to work and how you interact with it.
yeah, and maybe there's not as big of a concern as, will these things fit together?
Yeah, and that's a lot of what I've done in software is just struggle to fit things together and be like, okay, this thing can fail. How might it fail? How do I do a retry? How do I there's all these things that you then have to think about that are done differently. Whereas when you're in the Zio world, you have this thing, and now you have expectations about how it's going to work, how you do air handling, how you do retries. That and it's the same. It's universal across all Zio libraries. And so when you bring in one Zio thing, you bring in another Zio thing, you have the same expectations around air handling and recoverability and retries and all that kind of stuff. So
Mm.
having kind of that universal model, I think, makes it so that you can interoperate across different Zios more easily.
So it sounds like your observation is because these ecosystems have grown very rapidly, that suggests that once you get to a certain level of of your components and their reliability, then you do have higher productivity.
Yeah, for sure.
Mm-hmm.
Yeah, and we've always kind of wanted that Lego model
Mm-hmm.
of being able to just pull these different pieces together and have them work well together like Legos do. Uh, and we've we've seen pieces of that. Like I think that Spring definitely gave us a model that allowed us to easily pull together a bunch of pieces and wire them together. But there, I think that where that model fell down a lot of times was it didn't isolate the effects, and so uh, yeah, like there was always like places where, oh, this thing doesn't work like I expect it to, and so then how do I do error recovery on this thing, and then in the world of exceptions, and yeah, so yeah, I think we got a piece of that with Spring, but that Zio is that in a much better model.
Yeah, I just wonder how much people think about the problem. We're putting together this part of the language, and say in the case of Java, oh well, C++ has exceptions. We'll just use exceptions,
Yeah,
and not it's not really necessarily reasoned out that thoroughly what
yeah.
it is that you're trying to do. Um,
Well, and when I've done Spring, a lot of the programming ends up being in annotations,
mm-hmm.
and to me, that's not the best programming model because I want to program in in a language, and annotations are just metadata essentially, and so
Yep.
it ends up I'm moving a lot of the wiring and logic to this like metadata language that is on top of the main language.
And the compiler can only check so much of
Right.
around
Well,
your
and there's
annotations.
limitations on what you can do in metadata.
Right.
It's not the full blown language. Where
Mm-hmm.
one of the things I really like about Zio is it's just Scala. I'm not using some other language
Mm-hmm.
to write this thing. Whereas in Spring, I'm really writing two different languages. I'm writing annotations, which is not Java. I mean, obviously it is Java, but it's not the Java language.
It's not the Java language that can be checked
That
and
that's
and
right,
give you
exactly.
error messages and things like that.
That's right. Yeah, yeah.
Mm-hmm.
And so for me, I like the power of a general purpose language, and so
Mm-hmm.
that's how I want to write my code, not in some limited metadata form. And I certainly have run into places where I'm like, this metadata is insufficient. This metadata programming model is insufficient for what I want to do. And then you go into a world of hurt for how you how you take the escape hatch around that. It gets pretty messy. So I'd rather just start with, let's just write in the general purpose language and have it be able to be expressive enough where I don't have to make sacrifices on the expressivity that I want. Which the Spring programming model, when you're in the annotation model and it fits well with what you're trying to solve, it is very expressive. It's like, okay, give me this bean, and so that looks nice, but could we have that same expressiveness, but in the general purpose language? And I think that that's one of the main reasons I was attracted to Zio is that yeah, you get the expressiveness without hopping out to some other limited form.
Because you have to learn and understand that meta language.
And you have to learn the escape hatches and how to deal with them.
Mm.
And what do I do when the metadata form, when I reach the limitations of it?
So, sometime in the last week or so, I had what felt like a new insight about what monads were.
Oh yeah, let's hear
So,
this.
let me try. So, when you have a function, you can have as many arguments coming into the function as you want, but you can only have one result, one return. And so most of our functions historically have just returned some value. And so if anything goes wrong or if we want to do anything extra, we're sort of forced to do it using side effects. You know, we say if there's an error, well, in C they went through a bunch of different things where they tried to solve this. How do we report errors? And they go, well, you could return a -1. Well, if your function normally returns a -1, that doesn't work. Well, we could set a global flag. Okay, so there's your side effect.
There's your side effect.
Okay, well, when you call the function, you got to make sure you check that flag right away. And it's not going to work too well if there's concurrency, if more than one sets that flag or clears the flag or whatever. So they tried all these things, and the problem was that what we actually need is a bigger result, rather than this simple, oh, you're returning an int or a float or something like that. We need to return a package. We need to return this this box. And so that's the solution. And notice that Go took that approach. They go, all right, conventionally, you should return this box that has the success value or the error condition. Now, that's a good step because we've understood that we need a bigger package
more
to
information.
return. We need from that return value, and we don't want to be scattering it to the out, using side effects. But now every time you call a function, you get this box back and you got to unpack it. And that's the way it is in Go.
Yeah.
You got to unpack it and
if
check
error
it.
Not equal nil.
Every single function. And now our code is getting really messy.
Yeah.
And I can imagine people like wanting to take shortcuts around that or not doing it. Or
just forget to check.
Just forget to check. Just assume it's fine. So what we want now is some kind of system that automatically checks the result and unpacks it. And if it's not successful, well, we'll talk about that when we get to the exceptions versus monadic errors. So to do this in a uniform way, the mathematicians have discovered what this box and its operations should look like. And we end up in Scala with the for comprehension that you say for, and then this thing back arrow into my result, and this thing back arrow into my result, etc. And Scala has the mechanism built into the for comprehension to automatically unpack that result. And if there's a failure, it short circuits to the end. And the whole point of all this was just to be able to simplify the returning of these boxes so that it didn't make your code all horribly messy and stuff.
Yeah.
And that's the monad, is the box and the associated mechanisms to make the programming with the box easier.
Yeah. 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 And so there's essentially we have a flow,
mm-hmm.
and the with monads, we have taken that flow control and put it into the monad so that the person who wants to use that thing doesn't have to think about the actual flow control. But then we want the developer who's using this thing to be able to kind of treat this thing like it's imperative. Do this, then do this, then do this, then do this.
Because it's simpler to think about.
That's right. And the flow control mechanism in the monad will tell you, hey, I can continue doing things
Mm-hmm.
or not.
Mm-hmm.
Yeah, and I think that that was part of our realization when we were exploring this in some code was that monads, from all the ones that I can see, are essentially binary. There is a happy path and an unhappy path. There is a continue and a stop,
Mm-hmm.
and uh, and so there's this tree structure that can keep branching. Um, and the for comprehension in Scala says keep doing these things as long as you're on the happy path. So yeah, I
But
think
the
you're.
but the programmer doesn't have to be thinking about, oh yeah, there's a tree structure branching, and I have to. Well, it's
The
very.
flow. It's remember we at one point called it inversion of flow control or something like
Mm,
that. It's
mm-hmm.
like instead of the caller having to think about the flow control.
Which produces a kind of callback hell or a variation of
That's
it.
right. Yeah, or nesting of
Yeah.
ifs and
Right.
yeah, yeah, and so it's inverted it, and in the inversion, the monad is doing the flow control for you.
Mm-hmm. Mm-hmm.
So
So once it's set up, you have this nice syntax that is much more understandable than if you
in
had.
Scala you do.
Yeah,
So
in
you can
Scala you
certainly
do.
use monads without that nice syntax. I think
Then
one of the
it's.
nice things that Scala did was they realized that this should look imperative.
Mm-hmm.
And when you look at a for comprehension, it looks imperative.
Yep.
But you need that binary structure so that there's a continue and there's a stop.
Mm-hmm.
And at any point in your call, list of calls, operations that you want to perform, it can stop.
Yeah, and well, it it's easiest to think in terms of error monads when you're getting started. I mean, we expanded obviously after that, but when you look at what is the error monad trying to do, it's like, so you got a whole bunch of statements, any of them might fail, and what you're doing is you're saying, well, I don't want to have to do the error handling at each call. So what I want to do is move the error handling to a separate place, reducing duplication of code, separating the normal flow from the error conditions. And that turns out is exactly what we were trying to accomplish with exceptions. We were
That's
saying
right.
we were saying, okay, here's our normal flow of control. Now, if any of this fails,
Yeah.
the failures have enough in common, and that's what would establish what your try block was. You go,
Yeah.
okay, these are all similar errors, or they affect the same thing. So I can put all the error handling code for all of these statements over here in this separate space. And the only trick is, how do we jump from here to there?
Yeah.
Well, you put in an exception handling mechanism and it does all the thing and it keeps the stack trace for you and everything. And the error monad does the same thing. It says, we're going to execute a bunch of statements. If any of them fail, we're going to say, oh, those failures are similar, so we're going to have all the code over here. So it's solving the same problem. But with the error monad, and this is where I'm a little trying to figure something out. It's like, okay, so what is the difference? What benefits and downsides do we get? With an exception mechanism, you have it built into the language. In C++ anyway, the goal was for all of the exception handling overhead to be put when to only happen when the exception is thrown, and for normal flow control you
To
don't
not
pay
have the
for it.
overhead. Yeah.
You don't pay for it. And but now, I mean, in Python there are, like in the for loop, they use an exception to indicate that you're at the end of a for loop. Well, you'd never want to do that C++ because
Right.
all of the overhead is on
Yeah.
exception handling. Well, but in Python, they said, well, we'll make exception handling efficient enough in the overall
Yeah.
scheme of things so that you can use it in places for normal situations.
Yeah.
And so now we look at it here and we say, well, okay, with a monad, you can choose exactly how much information you want to capture from, where the exception, not the exception, the error takes place, uh, as much or as little, so you can make it as efficient as you want. So you could use the monad like for your normal flow of control instead of just exceptional flow of control.
Yeah.
Is that the big benefit? What
So
other
the,
benefits are
so I
there?
do look at error monads as being a lot like checked exceptions
Mm-hmm.
in that it is the caller has to explicitly deal with the fact that this thing can fail, and they know from the type, the generic type, how it can fail.
That's the checked part.
That's yeah, that is explicit. The main difference I think is that in air monads, your return value has the error or the success value in it. And so that's conveyed through the type system. Whereas exceptions are not part of the type system, they are some other thing, right? And so for me, just air monads are so much better than dealing with exceptions because it's in the type system. And then I can do all the wonderful type system things on those. You can even transform them. So you can say, all right, I can recover from this error. I called something, it returned something that can fail with this given error, but I don't want to return that to the next caller of me. And so now I can transform that error into something else. Maybe I can totally erase it, if it's totally recoverable, or I can ignore it or whatever. Then maybe I transform my air monad into just a value if I know that I can deal with it in some way. But it gives me a lot of uh, I can place a lot of expectations on something that returns an air monad, and I can chain them in a rational way, a way that is monadic. So chaining just works like I would expect it to.
So I think part of the type system is probably the key. And that allows, well, like Zio, I haven't experienced this, but you said Zio can do like this retry thing, where if something fails, it can say, oh, I'll just do it again.
yeah,
Whereas it seems like with exceptions, you've lost too much by the time you get to the catch clause
that's right.
to effectively do something like a retry.
Yeah, and it's not universal in that when you're in a monad, you have all the information that you need, or I should say, when you're in an effect monad, you have all the information of what needs to be done. And maybe it's even more general than effect monad. Maybe it needs to be a ZO because you have the environment as well as
Mm-hmm.
the error as well as the value. You have all three of those pieces, and so you can do a retry because you've separated out your environment from the operations that you want to perform on that environment. And so a retry is trivial and can be done. A retry can be done on any effect. You don't have to. You don't have to be like, okay, what exception did this throw? How do I get back in there with the same state that I went into it with? Like all those things that I've had to deal with in typical OO programming about retries goes away and becomes just a universal, easily applicable thing that I attach onto any ZO. So I think that's just one example of when I'm in a when I'm in ZO, so much of that stuff just becomes trivial because I'm working with pure functions that interact with an environment that is one of the type parameters. And the error type is something that I can look at and say, what is my error type?
Mm-hmm.
What do I want to do because of this error. So
Hmm.
yeah, it's it's a very different way of thinking about things. Um, but and there are, I think, different concepts kind of all muddled together that get us to this nicer place, because there's, you need to have the monads, you need to have the air piece of the monad, and then you also need to have the environment piece and separating out your operations from the environment. So there's a bunch of things that kind of build up to giving us this like really wonderful programming model for dealing with things that can fail, or things that talk to the outside world.
Okay. All right. Well, that helps me um, move forward a bit. Our next topic, if we're finished here,
Yeah.
is sort of the realization that type classes work kind of like default arguments. So there's this uh, argument that you don't have to specify when you call the function, and it gets put in there somehow by the, I don't know, the system,
Yeah.
whether it's the compiler or the runtime. But I think it's still the compiler,
It's a
right?
compiler in
Okay,
the case
so
of Scala, and
just
I've only done type classes really in Scala, a little bit in Rust.
okay.
So I'm not a huge expert on how everyone does type classes, but
Mm-hmm.
or other languages do type classes. But I can talk about Scala's. But yes, the way that Scala 2 did it, and Scala 3 does it differently, but I think the concept is still the same. Is that, yeah, essentially you've got your function needs some other thing, and uh, and how do you provide that in a way where you don't actually have to give it to the function explicitly?
But you can in special cases.
But you can, yeah. In Scala 2, it is just a function parameter. Type classes are implemented
An
as
implicit,
implicit function parameters,
right?
and so you can explicitly set it, or it can come in from the surrounding environment, which is like essentially just an import. Is the
Mm-hmm.
Well, there's multiple ways to provide that implicitly.
Somehow has to be in your namespace.
It has to be in scope.
Yeah,
Yeah,
in scope.
yeah.
So so which feels a lot like a default argument. And so
So the difference is that the default value of a default argument is provided by the function that defines it.
right.
And the reason why it is like a default argument, but it's provided by the surrounding scope,
Mm-hmm.
not the function that defined it. So yeah, I think thinking about it as default arguments that come from the scope, not from the definer, is a reasonable way to think about it.
So I guess, is there something, like if we were starting from scratch, would we have default arguments or would we always use type classes? Like, does it?
There definitely are times where I define a function, and I don't want the user to have to specify some default. Like this happens a lot with options. So I have a function that one of the parameters is an option, and I don't want the user to always have to put none in.
Sure.
If it, very commonly it's none, but sometimes it's some,
Yeah.
and so I just, as the definer of that function, I'll set the default value to be none.
To the most commonly used thing.
Right.
Right.
Yeah.
But you could also have accomplished that using a type class.
Then the user would have to import something that would fill that implicit parameter, and type classes need to be more specific than, like in my case, let's say I have an option of string. That's a very ambiguous type, and so I wouldn't ever want to make that my filled in by a type class, because there's a million things that could fill that particular hole.
You'd
And
have to maybe make it a type alias to something. You know,
I think that type aliases don't actually work for that, because
they just evaluate to string before the type class is substituted?
maybe uh, so I think that type aliases are just an alias, but I think maybe opaque aliases in Scala 3 may work for this,
Mhm.
um, but yeah, so I think that there's a difference between, do I want this parameter to be filled in by the scope, or do I want the function to provide me with a default? I think those are two different use cases.
Okay. So I guess, yeah, I guess maybe that's another way to ask the question is what are the use cases that default arguments don't solve? I'm trying to nail it, because it's a little vague. It's kind of like it's a design pattern where you don't know what uh, where do I apply this thing? How do I say no? That's a good application for a type class, and this one is a not a good application for a type class.
Yeah,
I'm trying to get a little bit more of a feel for how to use it in a design situation.
yeah,
And it seems like one uh, specifier is, well, here's a piece of code which might be common among more than one function. And so I want to pull it out of both of those functions and put it over here and have them use it, but it also needs to be modifiable. It also needs to be something I could say, oh, I want to use a different implementation here.
yeah,
So I could swap out implementations that would affect all of these different functions that use it.
yeah. Yeah, I think the common use case that I see for type classes is around generic transformers. So you've got something that needs to transform an A into a foo, just whatever into a foo of A or whatever. You've got some transformation from, maybe A to B is a better way to think about it, but some transformation.
And a bunch of functions are using this
A bunch
transformation.
of functions use this transformation, and the library may provide some transformations for you, like a transformation from string and from int, whatever, but the user may need to transform their own things. So they need to transform a
They've
bar.
created their own class and they want to provide a transformer
That's
for
right.
that thing.
Yeah, and
Okay.
so a bar may consist of a string, which needs to transform as well, but but we really want to transform a bar, and so I'm going to have to provide a transformer to anywhere that needs that's transforming an A to a B. I'm going to need to provide my transformer to it, and so type classes are the very commonly used, at least in Scala, way to define those
So there's
transformers.
this whole framework set up for using transformers, and I come along and I go, well, here's my stuff. And it goes, well, you can use your stuff without rewriting this whole framework
Yeah,
if you just provide a transfer, that
yeah,
that smallest piece that you need to actually change.
yeah.
Okay.
Yeah.
That feels like some new
There
thoughts.
there may be some other good use cases for type classes. Like we were talking earlier today about Zio Prelude and using type classes with algebraic laws,
Mm-hmm.
and kind of a different way to define what a monad is, and so maybe that kind of constraint oriented or law oriented way of thinking is another way to use type classes,
But I think a
another use
while
case. But
back we were also talking about something, and maybe this is only in Scala 3, where it can generate, you can have
uh,
rules and it can generate new type classes for you.
yes, yeah, that's
That
in
seems very powerful.
yeah, and so I I don't know a whole lot about this subject, but the words that people use around this are called GADTs. So this is oh gosh,
Like
based on generic
generalized.
generalized ADTs, algebraic
Mm-hmm,
data types,
mm-hmm.
and Scala 3 now has support for GADTs that will allow you to generate the type classes for whatever you want to generate.
So yeah, that makes me think the pattern is more around, okay, generate a new transformer and solve more of your problem without losing all the work that's been done that works with these transformers.
Yeah.
So
Yeah.
it kind of isolates the amount of code that you need to change down to maybe the minimum amount.
And people in Scala 2 libraries would typically use macros
Mm.
as a not as GADTs, because as an alternative to GADT, a way to generate your type classes for you.
Mm.
And so JSON is the most common usage for this, where JSON libraries, you oftentimes don't want to have to manually write a JSON transformer for a case class, for every case class that you're gonna be serializing, deserializing. And so macros will go and create the type class for you. But in Scala 3, it's a lot nicer with the GATTs.
Okay.
Now, without macros, you can do it, because now there's the metaprogramming built into Scala 3 that allows you to do that. I was thinking about Scala 3 equality and how now Scala 3 allows you to have to turn off universal equality. Universal equality is where in Java you can do dot equals, which takes an object, and so you can compare any object. And this leads to bugs because you can very easily compare the wrong things and not know that you're comparing the wrong things, and then you get a wrong result.
Because you can compare any object to any other object.
That's right.
It upcasts it all the way to object to do the equals.
That's right. And so in Scala 3, you can turn off that feature. Mm-hmm. And then to compare two objects, you have to have a type class available that says, yes, you can compare these things. But so this is more on the constraint use case of type classes, not on the transformer, because the type class that says I can compare an A and a B, it doesn't actually do the comparison. So it's not actually doing a transformation at all. All that it's doing is telling the compiler, yes, you are allowed. Here is the thing that fills that type class hole, and now you are allowed to compare these two things.
And that's why it's important that it happens at compile time.
Yeah.
Right. I see.
Yeah. And in Scala 3, when you do this, it still does use the dot equals to do the comparison, but you don't get the ability to call dot equals on things that you don't have the type class for. So in that case, type classes are used as like a compile constraint, which says you must have this thing in scope. I think it's even called can equal. So can equal has two type parameters. So you say foo can equal bar, and if you provide the type class for that, then the compiler says, great, I will let you do equals on these things.
I see. So it actually provides information to the compiler.
Yeah.
Simply by its presence or lack of presence.
That's right. Yeah, it's
right.
And if you have not provided something to fill in that parameter, essentially, then the compiler says, hey, no, you're missing something you need here.
So it can give you a good error message about it.
Yeah, and in Scala 3, the error messages have gotten a lot better because the type class support is now it's now an actual thing instead of just relying on implicits. Because in Scala 2, if you don't provide the type class, you get an implicit not found. Like, it's just like, hey,
what does that mean?
Yeah, exactly. Yeah. Whereas in Scala 3 now, it's like, hey, I need you to bring into scope this exact type.
Okay.
Much more rational.
All right. So it's not completely internalized type classes. I think it's going to be a while before I completely grok it, but this is much better. This is helping. So
good.
So
and then Cody's question.
Yes, Cody asked. He sent me an email asking about design patterns, and he's been programming. He finished a degree in computer science here at Western, and he's been programming for a few years since then. So he's kind of finding out about them. And he asked me, like, is this a thing? It looks cool. Should I really, dive into this? What are the good design patterns and all
Yeah.
that?
Yeah, it's a really good question. Josh Surratt and I did a presentation a couple times about the future of OO programming, which was kind of just about functional programming. But one of the things that we talk about in that talk was that there seems to be this cycle of, all right, programming language invented. We find some deficiencies in the language for solving the problems that we want to solve. So we create patterns to fill those gaps or make certain things easier. And then the language or other languages iterate and take some of those design patterns and build them into the language so that we no longer need the patterns.
And that's sort of the design patterns represent language failings school of thought. And I would say that's an interesting analysis, but I feel like it's a little heavy handed because there are some things where you go, in special cases we use this, but we wouldn't use it enough it wouldn't be justified to incorporate it into a language. And then there are other cases where it's really just, well, so I'll give you an example, what I consider one of the most basic design patterns. So you're in a base class. You have a function that does some basic operation that isn't going to change, but it calls one or more polymorphic functions, which are also defined in the base class. And when you inherit something, you might redefine those. But this basic, and I've forgotten the name of this pattern, even though, yeah. So I used to write a lot about these and teach them.
Is this delegation? Delegate?
No, it's not
No.
delegation. It's I don't know. It's something really basic. I've
Okay.
forgotten it. So, but it's like, well, that's just a basic way to write code using an object-oriented language, so that you're not, that you keep the code that's common in one place, and you have the code that changes in the redefined polymorphic functions.
Right.
And I don't know how you would incorporate that into the language any more than it already is.
Yeah.
So that's a
Yeah.
counterexample of.
Would you call that a pattern?
It is. It's in the Gang of Four.
Huh.
Yeah, yeah. It's a basic.
That just seems like
Exactly, exactly. But they thought, oh, yeah, it's OO, and it's like separating the code that changes from the code that stays the same. It's really.
So type classes, I think, are a better way to do this.
Well, yeah. It's a different form of polymorphism.
Yeah.
And
Yeah.
that was another thing that I came across in the.
So I think so. Back to this, I think this is important because I think that what you're pointing out is a design pattern for OO. I'm saying we discovered a better way to do it, and we, like in Scala 2, we did it kind of ad hoc using features that existed, but then at Scala 3, it actually became a language supported feature. And so I think that this actually fits that cycle of like, okay, what's the problem that we're trying to solve? And we needed a pattern to solve that problem.
Right.
And then we found a better way to solve that problem. And then we took that pattern and made it a language feature.
Yeah. Oh, I see. So you're saying that type classes would be the language feature that does what I just described.
Yes.
Which I'm looking it up on this.
What the actual name of the pattern
is. Yeah. Let's see.
Facade.
Proxy facade. No, it's not that. It's maybe it's behavioral. Template method.
Template method.
That's what it is. Yeah, it's called template method. So,
oh, and so interesting that they use data transformation as the example there.
Right.
So yes, so the template method pattern, it worked around a deficiency in typical OO, and so I'm sticking with my philosophy that we found a better way to do this, and it is type classes. And
Mm-hmm.
now there are languages that have type
Okay.
class support in the
Yeah.
language.
Yeah. I guess when you're in the box of, like C++ and Java, and your only tool is inheritance polymorphism, then you go, well, that's how else would you do it?
That's right.
And then when you say, oh, well, we have the common code here, and then you have these, say this method that gets overridden to show the variance, and you go, oh, well, instead of inheriting and overriding that method, you simply stick a type class in there.
Yeah.
You simply do this kind of compile time composition. Could that be the way you think of it?
Yeah, yeah. I mean, it's just a different form of polymorphism, right?
Right, and
It's
that's something I came across in the Red Book, where they said something like, I forget exactly how they put it. I think they said polymorphism is the function behaves differently for different types, but then I started thinking maybe it's just that the function can accept different types. How it behaves is up
yeah,
to it,
yeah,
but being able to and that works with generics as well, because you're accepting different types.
yeah,
So I don't know, I'm still kind of redoing my uh
yeah,
trying to broaden my definition of what polymorphism is.
yeah, yeah.
But
It'd be interesting to go through all these design patterns and see like which ones are no longer needed because of Java language
mhm.
features, which ones are no longer needed because of Kotlin language features, which ones are no longer needed because of Scala language features. That's obviously the languages I know best, but
And I
um,
should I should also point
it's
out,
like the visitor pattern that
yes.
that goes away, like with pattern matching and um, Josh and I talked about it in our talk, and I don't remember all the details on it, but we're like, yeah, the visitor pattern gone. Like we don't need that. We don't need that pattern anymore. And I think it was with primarily with pattern matching, but I forget if there was another aspect to it. Maybe it was type classes and pattern matching or something, or
Yeah,
ADTs and pattern matching. I
because
don't
a lot of
remember what
times
it was, but
people confuse the visitor pattern. I mean, and it's messy and complicated.
yeah,
Um, it's basically, what you want to do is be able to add functionality as if it requires certain constraints. It says, okay, you have an inheritance hierarchy that's fixed, and now you want to add it. What you want to be able to do is do something like, in effect, add new um, polymorphic methods in the base class. And that's why you have to have the visitor mechanism. But to do that, then you have this separate hierarchy where you're adding
right.
these polymorphic. So it's really
So maybe extension
complicated.
methods or
And yeah, and it's like and a lot of times people misunderstand it. I did want to mention the website that we were looking this up on is refactoring.guru, and they have done a really nice job of putting all the design patterns up there and explaining them, and lots of diagrams and everything.
yeah,
Just super nice job.
yeah.
So
So for Cody, design patterns are definitely useful, but I would say that they're always changing. And
well, that's the other thing,
as
is
languages evolve,
the Gang of Four book, which has the 22 patterns that they show on refactoring guru. Well, I mean, not
how
all of
many of
those,
those do we even use anymore?
right? Some of them, and in the end, it's like, well, some were. I mean, how many people use visitor? That's a very kind of a weird constraint in
Yeah.
some ways. I mean, the thing is,
Well, Gang of Four was even before generics, right? Like,
I
I
think it
think
was.
generics, I think just generics alone made it so some of those patterns
Mm-hmm.
were no longer necessary.
Yeah, yeah. So I mean, that's the other thing, is like, when this site takes the gang, or what I did is, most of the patterns that I talked about were Gang of Four patterns. Some were outside of the bounds, but I mean, you get this impression that, oh, well, these are the patterns, but those were just the patterns that were important to
Of
them
that
at the
day.
time,
Yeah.
and half of them, I think some of them were in Smalltalk, and some of them were in C++. None were in Java because it predated Java. So it's
Yeah.
like you have to, and then there are other books that came out that had different patterns in them and stuff. So it's like, it's really kind of a messy thing, and I do. I think I did find it as an intellectual exercise. It was helpful. And there were times that you come across a design and you go, oh, yeah, this might be this pattern or that pattern. But does that happen all the time? Or is it worse because sometimes people will go, oh, look, I used all these patterns. And it's like, well, did you need to use the
Right.
patterns? Or are you using them just because you want to check some boxes on your
I've
resume?
definitely have built a lot of systems where I just used the patterns because that's what I thought I was supposed to do.
Mm-hmm.
And yeah, it's definitely not the right way to do things.
Yeah.
But it's also really hard to know when you should and shouldn't. That takes experience and wisdom, which
Often
you have to get there somehow.
you have to play with the problem for a while to see, oh, where is it? I would use this term, the vector of change, and say, what's changing in the system where I might need to redesign it so that the change happens easier. Like basically, well, am I adding new types to the system that and I need to modify my code so that it's easier to add new types to the system?
Yeah.
Or is some other structure changing? Or are we not just doing JSON? Are we doing all these other formats as well? Oh, well, then we need to change our system to make that easy. So you almost have to work with the system long enough that the pain points start to appear.
Right.
And you go, oh, the pain points, so that's where I might, well, look at a pattern or figure out how to
Yeah.
design around that to make it less painful.
All right. Well, that was fun.
Yes, it was. And hopefully our new equipment provides a better listening experience.
Yeah, we'll find out. Let us know on our Discord channel.
Yes, please.